I'm going to show you how we quantitatively test the different Maillard reactions between, well, in the original lab, 4 different amino acids and 6 sugars. I did 2 amino acids and 2 sugars as an example. I used, here's my little chart, lysine and glutamic acid and sucrose and fructose. So that gave me 4 different test tubes. I made these 50 millimeter solutions in a 9.5 pH buffer. So I took, for example, 14.6 milligrams of lysine, and for solution 1, sucrose, 34.2 milligrams of sucrose, and mix them in 2 milliliters of buffer. So here's 14 milligrams, is not very much, of lysine. Now, if we were making them for the whole class, it'd be a lot. Make stock solutions and share, but since I was just doing an example, I just made enough for single batches. So this is 34 milligrams of sucrose and 2 milliliters of the 9.5 pH buffer, carbonate buffer. Put that in there. And then mix them up for a few seconds until it's all invisible. A little more. Looks pretty clear. So then I brought it over here to the 90 degrees Celsius water bath, and stuck them in here. They've been in here for 30 minutes. You can see 2 of them, or you will see 2 of them, look pretty brown. I'll get rid of this one. We'll focus back on that was at 90 Celsius for 30 minutes. Pan in to the test tube rack, and I'll get a better look of how they turned out. So here is solution number 1, lysine and sucrose. Solution number 2, glutamic acid and sucrose. Solution number 3, there's some browning, fructose and lysine. And solution 4, fructose and glutamic acid. Now 1 and 2, at this point, I would say we could leave in for another half an hour to see if it eventually does something, or maybe go back and check. Common between 1 and 2 is the sucrose. That could take some further investigation to see why it's totally clear, no apparent browning. We can also see if there's any browning using the spec here. We have the Genesis visible spec. So I'm going to bring you over here to see our spectrophotometer. Zoom out. So this device has a light bulb inside. Come up, and I'm also going to turn the lights off to demonstrate how it works. Do a top down, so you approach it right here. It has a lamp inside. Open this up, and there's a little spot where you can put in it's called a cuvette. It's just a little sample holder. This cuvette has a piece of chalk in it, so we can actually see the light is going to come in this way, and then there's a detector to see how much light is going through your sample. So when I put the chalk in, none of the light will go through the sample. So the absorbance is going to say infinity or something, but it's just to show that there's a little specific color. Let me turn the lights out so you can see better. Okay, here's our, so right now we're set to 658 nanometers. That's the wavelength of light coming through. And you can see that's, whoops, like my record button is interfering. Hopefully it's not super loud. So it's brushing against the microphone. 658 nanometers corresponds to red light, and you can see the red light coming through there. Get this lined up a little better. So that's the red light shining against the chalk. I'm going to decrease the wavelength, and we should go through the whole rainbow. So there's a prism inside. You see it go through orange. That splits the white light into different colors, and then a arrangement of mirrors that can let us adjust exactly which wavelength out of the whole spectrum we want to pass through our sample. So now it's going through green. It's at 581 nanometers right now. Switches, different set of mirrors. Keep going down through bright green, 520. Turning towards blue around 500 nanometers. That's 475 nanometers. And then Roy Biv, indigo, and violet down here in the low 400s. So this is 436 nanometers, probably indigo. You get the idea. Okay, let me turn the lights back on. Hopefully you can see the screen. Okay, so in the lab manual it says to use, sorry, just had it here, 360 nanometers. Oh, so go even a little farther. 400, 360 nanometers. Can't even see a dot there. Could be in the UV. Okay, so I'll take out the chalk that we used just to show the color that was passing through. And I'm going to put in a sample of just deionized water, so this is pure water. And I'm going to use that to set the blank. So I'll put that in here, close this, and I'm going to say press the 0 ABS button. I'm telling it that that should be 0 absorbance. And it's calibrating. Okay, 0. Now we're going to test solution number 4, which was glutamic acid and fructose. So I'll pour some into one of these cuvettes. Doesn't take much, a couple mils. And I'm going to swap that out for the blank, making sure that this, once the long side is, the beam of light is going through the long side here. Sorry, you can't see. So it has a 1 centimeter path length. I want that to be the same for all the samples. Put that in there, this, and this will tell me the absorbance. Greater than 2.659. Struggling. Let's try another one. That was 4. Let's see if 1 and 2 are giving us any measurable absorbance. This is solution 2, which was glutamic acid mixed with sucrose. Looks clear, but let's see. Very little, 0.002. Okay, let's try the most brown solution, solution 3, lysine and fructose. Fill up the cuvette, Place it in the path of the beam in between the lamp and the detector. And it is higher at around 2.7. I think they're a little too dark. I'm not getting the best readings. For completeness, we might as well do solution 1, see if that, even though it looks clear, shows any absorbance. And we do have some, even though we couldn't tell the difference between solution 1 and solution 2. Solution 1 is showing 0.017, whereas for solution 2 we had 0.002. So I think the next step would be to dilute solutions 3 and 4 to try and get a more accurate reading, try to bring the absorbance within the range that the machine is capable of measuring.